Hello. Good evening. So today I am going to discuss model adequacy checking. So today I already discussed adequacy checking. Already I have discussed this topic in a simple linear regression setup. So here I discuss generally and more deeply. Okay, so we know the fitting of linear regression model, estimation of parameter, testing of hypothesis. Okay, can you Sir, I have a doubt from previous day class. What is the interpretation of adjusted R square? Okay, adjusted R square. Actually, adjusted R square. We have used adjusted R square for multiple linear regression model. If you add, in the case of multiple regression model, if you add more explanatory variable, automatically value of R square increases. But the additional variables, explanatory variables, may or may not be influential. But adjusted R square gives you provide the actually adjusted R square used in that situations, and this actually I am going to say in the case of so adjusted R square increase when the influential explanatory variables have some influence. Okay, so so for multiple regression model we compute not only R square, also adjusted R square. Here or not? Please tell me. Are you satisfied? Actually, R square always increase if you add explanatory variable, but whether this explanatory variable has significant effect or not, if you add this influential variable in the model, it is always, your R square is always increased. So, but adjusted R square gives the increase when only the added variable have some significant influence. Okay, so multiple regression model, we need adjusted R square along with R square. Okay, can I continue or not? Please tell me if you satisfied with my answer. Please tell me. Are you satisfied? Yes or no? Paulika Pal? Okay. So, model adequacy checking. The fitted linear regression model, the estimation of parameter, the fitting of linear regression model estimation of parameters testing of hypothesis properties of the estimators are based on following assumptions. And we know these assumptions. Assumption number one, the relationship between the study variable Kovika, are you satisfied with my answer? Please response. If not, I explain you. Kovika, I am asking you. You asked me, sir, I have a doubt from previous K class. What is the interpretation of adjusted R square? Please tell me. Can I explain? If you need more explanation, I will explain you. I have no problem. Please see the expression of R square. R square means what? Sum of square due to regression divided by SS due to total. Okay. So if you add more explanatory variable, whether these explanatory variables may significant or not, whatever the status of this explanatory variable, your SS due to regression always increase for adding new explanatory variable. Okay, for adding new explanatory variable. So if you add more explanatory variable, then your SS due to regression increases. As a result, your R square always increase for adding new explanatory variable. But this additional explanatory variable may be help significant or not. Okay, if it is not significant, even if your R square increase, you can say using R square you can say your model is good, but in reality your model is not good. But adjusted R square increases only when this adding this new variable is significant, is or are significant. So if your adjusted R square increases significantly, this means your additional new variables have significant effect. Okay, Koulika, are you agree or not? I already give the expression of adjusted R square. Please give me a 5 minutes, I will back. Okay, I have a call, I will back. So, sorry. Uh, so, can I start? Okay. So, I think you agree with my answer. So, for that reason, we use not only R square, also compute adjusted R square when you use multiple regression model. Okay. So, please join. Okay. So, the relationship between the study variable or dependent variable and explanatory variable or independent variable is linear, or at least approximately. Secondly, the error term has zero mean. Thirdly, the error term has constant variance. Fourth, the error are uncorrelated. Fifth, the errors are normally distributed. Okay, we know these things. So, the validity of these assumptions is needed for the result to be meaningful. So, if you apply linear regression analysis, before applying linear regression analysis, you need to check these 5 assumptions. Okay. And if these assumptions are violated, the result will be incorrect and may have serious consequences. So, we need to write this thing. If these assumptions are violated, the result can be incorrect and may have serious consequences. And if this departure are small, the final result may not be change significant. But if this departure are large, the model obtained may become unstable in the sense that a different model with opposite consequence opposite conclusion. Okay, opposite conclusion. Therefore, such underlying assumptions have to verified before attempting to regression mode. Regression model. First, check the procedure is first you check checking of linear relationship between study and explanatory variable if there is a single explanatory variable, so we know we draw a scatter plot. If the scatter plot look like this, we know there is a positive correlation, and if this like this, then in that case we know this means that there is a negative linear relationship between these two variables, that is the study variable and explanatory variable, and if it is look like this means there is a non-linear relationship. We know this thing. Okay, but in the case of more than one explanatory variable, okay, in that case we need to draw scatter plot matrix. Scatter plot matrix. Okay. need to draw scatter plot matrix. It is a two-dimensional array of two-dimensional plot where each form contains a scatter diagram except for the diagonal. Thus, each plot set some light on the relationship between a pair of variables. It gives more information than the correlation coefficient between each pair of variables. Because it gives a sense of linearity or non-linearity of the relationship and some awareness of how the individual data point are arranged over the region. For example, actually, it is a scatter diagram. It is a scatter diagram of, suppose I have a k explanatory variable. In that case, this is a scatter diagram of yx1, yx2, yx3. Another opinion actually are another options. Better to write another option to present the scattered plot is scatter diagram, not scatter plot. Scatter diagram is present the scatter plot in the upper triangular part of plot matrix, or and mention the corresponding correlation coefficient in the lower triangular part. So can I go to the next slide? Subhrojit, Konika, please tell me, can I go to the next slide? Arun asked me, that the link you provide for assignment expired from very first day. How will you? Okay, Arun, no problem. I will provide another link. Okay. So please, all if you have been facing such problem, please tell me either phone or WhatsApp, or you can send me a message through WhatsApp. Okay. Thank you. I will definitely provide the link within a few days. So suppose I consider k equal to 2, there are two explanatory variables. So in that case, this plot so this is y, so this portion is empty, and suppose this is a scattered diagram yx1, this is yx2, And here this is a correlation between x1 x2. So if you look at this, I think it is minus 0.7, almost equal to minus 0.7. You can, if you compute this and write this value here, okay. And this is 0.3. I assume that this is just an example how to represent this scatter this matrix plot, okay. So this plot look like. So from this arrangement you can easily see that the relationship between study variable y with x1 and x2, and also the relationship between study explanatory variables x1 x2. So from this matrix plot we can easily find out the relationship, this relationship, okay. So next assumption says that is the error term has 0, the error term has constant variance, the error term are uncorrelated. So first I check the error term has 0, mean and error term has constant variance. So for this we need residual analysis. The residual is defined as the difference between observed and fitted value of study variables, that is yi equal to yi minus yi hat. Yi is a observed value, ith observed value, and yi hat is a ith predicted value, and this gives the ith residual. Now we can use, instead of ui, scaling residual. So the method of scaling residual this is a standardized residual. First I define standardized residual. So this is defined as ei by root over MAC due to residual. The idea is this is a it look like a jet score, and since MAC residuals gives the unbiased estimator of sigma square, this is a standardized value of EI, and we denote it by DI, okay. And we see that the expectation of DI, this is equal to 0, and variance of DI, which is approximately 1. You can check using the distributions of EI and MEC, SS due to residual. Okay, you can check this thing. So for large, and we know if Zi lies between -3 to +3, then there is no outlier. If Zi is greater than, Zi means Z score, Z score is greater than 3 or less than -3, we can say that this indicates there is an outlier. We know this thing. Okay, there is another technique of checking outlier. We can check either compute lower whisker or lower fringe, or upper whisker or upper fringe, or compute the Z score if your data if you see that your observations come from symmetric distributions, bell-shaped distribution, in that case you use Z score technique for finding outlier. And if you see that, since using empirical rule, we know, sorry, so we know (99.7%) of data using empirical rule. We know 99.7% of data lies between -3 to +3, and the very few number of data lies below -3 or above +3, and the data means here Z score. That means if we convert our data to Z score, that is value or observation minus mean by SD. And if you see that number, if there is a data point which is greater than 3 or -3, this means this value, we can consider this value is an outlier. So I use this technique here. So first I convert residual to a standardized residual, okay, and then we check that if a large value, so a large value of Di greater than 3 or small value of Di less than -3 indicate potentially an outlier. I think it's right in that way. Potentially indicate an outlier. Okay, so if you convert your EI to Di, and if you find that there is some value which is greater than 3 or less than 3, then you may less than -3, then you may consider this value as an outlier. Okay, so next thing is studentized residual. We know the hat matrix. I already defined this hat matrix H, which is equal to x prime x inverse x prime, whose ijth element denoted by small hij So the and we know the variance of E curve, which is equal to I minus H sigma square. So this implies variance of EI equal to 1 minus HII sigma square. And covariance of EI comma J, which is equal to minus Hij sigma square. Since 0 less than HII less than equal to 1, so if you can find this value, because variance of EI is greater than equal to 0, this gives HII less than equal to 1, and again you see that variance of beta curve, which is equal to H sigma square. So from that you can get HII greater than equal to 0. Okay, so we can write HII lies between 0 to 1. So MSD to residual is used to estimate variance of EI, then variance of EI hat, so this is equal to sigma hat square 1 minus HII MS due to residual 1 minus HII. This implies MS due to residual overestimates the variance of EI. So see that in standardized residual I use sigma hat square. I replace sigma hat square by MSC residual, where sigma hat square is nothing but a C. Actually here I use Z score. So Z score is observation minus mean, because mean of EI equal to 0. So EI divided by SD, standard deviation, which is root over sigma square. Since sigma square is unknown, we replace sigma square by sigma hat square, and I use sigma hat square is a MSC due to residual, but it should be EI by root over V hat EI, but here we see that this variance of V hat EI is nothing but a sigma hat square 1 minus HII, and since sigma hat square is equal to MSC due to residual, sigma hat square is MSC due to residual, so this is equal to MSC due to residual into 1 minus HII. So since HII lies between 0 to 1, HII lies between 0 to 1, this means this is less than equal to MS due to residual. So here I use, instead of variance, instead of the unbiased estimator of V hat EII, I use overestimate of variance of EI, because sigma hat V hat EI. Okay. So instead of using V hat EI, I use I use this sigma hat square 1 minus HII, which is logical. So I write a logical procedure is to examine the studentized residuals of the form Ri EI by root over Ms residual 1 minus HRI. Okay. And we see that expectation of Ri equal to 0 and variance of Ri equal to 1. So please tell me, have you any doubt? Okay. So see, again I illustrate this fact. In standardized residual, I use simply EI by root over MS due to residual. And actually, if you use jet sport, this means you should use EI by root over variance of EI, and if your variance is unknown, you replace this by root over variance of EI. So here I use overestimate of variance of EI hat, because MS due to residual we see here is a overestimate of variance of EI. So studentized residual remove this overestimate by using MS due to residual 1 minus HII. If you use this thing, this is the unbiased estimator of variance of root over of EII. So the logical approach is you use Ri instead of Di, which gives a and if you use Ri, then you see that the expectation of Ri is 0 and variance of Ri equal to 1. But here we see that this variance of Di, which is close to 1, it is not exactly 1. Okay. So Oyun, have you any queries? Subhajit, please tell me, have you any queries? Oyun, Subhajit, Paulika, okay, Subhajit. So hence any point with a large residual and large HII is potential highly influential on the least square feet. Hence, examination of RI is generally recommended. Can I go to the next slide? Chundrima, thank you. So please tell me, can you go to the next slide? Subhajit, tell me, can I go to the next slide? Okay, thank you. Trace residual the trace residual are defined as yi minus yi hat, where yi hat is the fitted value of the ith response based on all the observation except the ith one. That means you have a data set y1, y2, yn. I write in vector form, and this is your matrix, data matrix x11, x12, x1p corresponding to y1. This is your yi, xi1, xi2, xip, xn1, xn2, xnp. So just eliminate this portion and fit the model using remaining portion. That means y1 to yi minus 1 and yi plus 1 to yn. Similarly here also, using this data set, you fit the model. Suppose using this data set your estimated model is since I eliminate I portion, so I write I here within first bracket. Okay, so if you put the so this gives the this is the fitted equations where I portions is excluded except the I portions, the, and in that way you get this y I hat is the fitted value of I response based on all observation except I. Okay? The reason is if yi is really unusual, suppose your yi is really unusual, then the regression model based on all observations may be overly influenced by this observation. This could produce a y hat that is similar to yi, and as a result or consequently corresponding ei will be small. So it is difficult to detect any outlier. If yi is detected, then yi hat cannot be influenced actually. Again I say I need to clear this portion. So using this remaining data set you can feed this model Okay, it's better to write. Okay, no problem. This means I stood ith observations. Okay, you feed this model. Now for xi curve, that means xi1, xi2, xi p, I think it is better to write this. This is the fitted model based on the data set where ith observation is excluded. Okay, so you get y hat star I and I denote this by yi hat. Okay, so this is the yi hat, and in that case yi hat cannot be influenced by that observations. Why? Because if your calculation or your yi is involved, in that case your all predicted value influenced by yi, and if you eliminate this yi, then this yi is not involved in your calculations. Hence, your predicted values is not influenced by this yi. So yi hat cannot be influenced by these observations. So the resulting residual should be likely to indicate the presence of the outlet. And the procedure, just I need step by step procedure how to compute yi hat. Step 1, I already mentioned this, delete the ith observation. Step 2, fit the regression model to remaining n-1 observations. Then step 2, first step, calculate yi, calculate the predicted value which I denoted by yi hat, yi hat, where we write I within bracket, first bracket, calculate the predicted value of yi corresponding to the deleted observations. Then step 4, we calculate yi, which is equal to yi minus yi hat, where I written in bin first bracket. Now we can compute all such type of ei for all in observations. And check that this is your homework. This ei is nothing but a ei. This is a deleted residual, and this is a usual residual ei, which is nothing but yi minus yi hat, where no observations are deleted, ei by 1 minus hi. Please check. This is your homework. Therefore, you see that EIs are just the ordinary residuals weighted according to the diagonal elements H, II of capital H. Therefore, it is not required to fit different regressions. So, for computing EI, you just to compute EI, E within bracket I, you just compute EI and 1 minus HII, this gives EUI. So, you do not need to compute YI hat where I written within first bracket. You do not compute this for all I. So, because if you compute this, we need to fit n equations, n different equations, and in these steps you delete the corresponding observation and fit the regression model, and then you compute y hat I within first bracket. So it is a very laborious thing. Instead of doing this, you just compute this, and this is, and you can compute this only computing single equation, single regression equation. So this formula helps you to compute E within bracket first time, within first bracket I. Okay. Shubhrojit, sir, how to understand that YI is really unusual? Okay, Shubhrojit, so that's why I compute. First I answer your first sentence. Okay, you write, sir, how to understand that YI is really unusual. So that's why I do not know whether YI is unusual or not. So that's why I compute n regression equation. First regression equation I delete y1, second regression equation I delete y2, so on. So I compute all n regression equation and I compute all n y1 hat, y2 hat. Okay, and then I compute e1 hat, e1, e2, en. Then I check whether this E1 is influential or not. If E1 is not influential, then you can say Y1 is not influential. If E2 is not influential, you can say Y2 is not influential, and so on. So for all n, you need to check. So if you find your ith observation is influential, after computing all these things, then you can say your yi is influential. Okay. Sorry, there is a problem. Please give me a time. There is a technical problem. Please give me a time. Okay, you understand. Okay, so there is a technical problem. So, Subhajit, I think you can understand what I want to say. So, you need to compute all this thing and then you find which observations is influential. Okay. I think there is a problem. Please give me time. So, okay, now it's fine. So, here we see that the residuals associated with points for which HII is large will have large trace residuals. Such point will generally be high influential point and here we see that variance of I within first bracket equal to sigma square 1 minus HII. Please check, this is your another homework. And then the standardized trace residual equal to E within first bracket I var of E within first bracket I, which is equal to sigma, sigma square by 1 minus HII. And since our, and this is this EI within first bracket is nothing but a, you see that this is nothing but a EI by 1 minus HII, see this portion. So we write this as EI by root over sigma square 1 minus HII. Since sigma square is unknown, since sigma square is unknown, we estimate this by mean sum of square due to residual. So can I go to the next slide, Shubhajit, Oyom? If you hear me, please tell me. Can I go to the next slide? Subhrojit, Sundrima. Can I go to the next slide? Okay, thank you, Subhrojit. So another approach is to use an estimate of sigma square based on data set with ith observation removed. Say, I denote this by SI within bracket I square, and we compute SI I within bracket first bracket SI square as 1 minus 1 by n minus k minus 1, because here I use n minus 1 observation, not only that, this is the error degrees of freedom when in the regression there is a k explanatory variables. J curve, this is a row vector, Vj curve is a column vector whole square, and this gives
This is divided by, okay? This is the divided by n minus k minus 1. This estimate of sigma square is used instead of ms due to residual to produce an externally studentized residual, usually called R student, given by Ti Ei by root over Si square 1 minus Hii, and I from 1 to n. In many situations, this Ti will differ little with Ri. However, if ith observation is influential, then the Xi square can differ significantly from ms due to residual and the R student statistics. And the R student statistics will be more sensitive to this point. Under usual assumptions, usual regression assumption, T follows a T distribution with n minus k minus 1 degrees of freedom. And we know the residual plots. We already discussed this residual plots. This is a graphical analysis of residuals. Is a very effective way to investigate the adequacy of the fit of the model. We already see this thing and check the underlying assumptions. Here it is better actually it is need for adequacy of the fitted adequacy of the fit of the model of a model and to check underlying assumptions. It is better to plot the original residuals as well as scaled residual or pi, di, etc. scaled residuals. So we already defined this thing. Original residual as well as scaled residuals typically the studentized residuals are plotted as they have constant variance. Initially, I cannot understand, sir, what is Ri? I already defined Ri. Yes, yes, Shubhajit. So please let go to the previous slide. So okay, what is your question? Vishali, I cannot understand your question because I already defined Ri. Please check the previous slide. And Shubhajit, in the regression of SI, okay. Yes, yes, you are right. Actually, and this is nothing but a yj. These are all obtained from using least square technique. Okay, just see. You use y1, yn excluding yi. Just use this, and similarly here also same thing, and compute this portion. Okay. Shubhajit, okay, thank you. So the studentized residuals are plotted as they have constant variance. Okay, it has constant variance. So now go to the, I already discussed normal probability plot. Here I give, okay. So see, figure A, I discussed this figure. This figure has an ideal normal probability plot points lie approximately this reference line on the straight line and indicate that the underlying distribution is normal. So if your plot look like this, then you can say that your assumptions of normality holds. Okay. Now go to the figure B. This figure has a sharp upward. This is a sharp upward. Sharp upward. And downward curve. This is a downward, sharp downward. So this figure has, I write this as, this figure has sharp upward and downward curves at both extremes. This indicates both extremes. This indicates that the underlying distribution are thicker than the tails of normal, thicker than the tails of normal. So this indicates that the underlying distribution thicker than the tails of normal. This means this distribution is heavy tail distribution. For example, heavy tail distribution means log normal distribution, Pareto logistics. These are heavy tail distributions. And in this figure, figure C, this figure has flattening at the extremes for the car this indicates that the underlying distribution is light tail. That is, the tails of the distribution are thinner than the tails of normal distribution. For example, exponential, Gumbel, these are the example of a light tail distribution. Okay, and I already discussed this type of figure D. This means this indicates there is a positively, this is the positively skewed distribution. So this figure has sharp change in the direction of train in in upward direction from the mid upward direction from the mid. This indicates that the underlying distribution is positively skewed. Yes, I mentioned this thing. Figure 2 is a habital. Habital means logistic, Pareto, log normal. These are the all example of a habital distribution. Okay, I already mentioned. Please listen carefully. Okay, no problem. You are absolutely right. Right. I already mentioned this distribution. I also mentioned other two distributions. These are all habital. That is Pareto and log normal distribution. These are also the habital distribution. Okay, Ayun. And this figure has sharp change in the direction of trend in downwards from the mid. This indicates that the underlying distribution is negatively skewed. See that? This is the middle portion, and then see that downward direction. Strain is downward direction. Okay. Therefore, some experience and expertise is required to interpret the normal probability plot, because the samples taken from normal distribution will not plot exactly as straight line. Okay. Now, yeah, please note down some points. When samples, for small sample size, that is your sample size n less than equal to 16, small sample size when n less than equal to 16 often produce normal probability plots that deviate substantially from linearity. Large sample size when n greater than equal to 32 produces plots which are much better behaved. plots which are much better behaved. Unusual, and when n equal to 20 is required to produce stable and easily interpretable normal probability plot. Okay. So first of all, for small sample size, when your n less than equal to 16, produce normal probability plots that deviate substantially from linearity, and for large sample size, that is when your n greater than equal to 32, produces large sample size produces plots which are much better behaved, and when n equal to 20, then it is required to produce stable and easily interpretable normal probability plot. So now, similarly, we see same thing for, next we consider so this is a residual versus fitted value. Y hat is the fitted value, and this is the along y axis we plot residual, that is Zi. This is plot of residuals versus fitted value. Okay. So here I use EI, you can also use scaled residual RI, PI, etc. and interpretation are same. So first I consider figure A. If plot is such that the residuals can be contained in a horizontal band fashion, this is a horizontal band fashion. Okay. And the residual fluctuates, you see that the residual fluctuates is more or less in a random fashion inside the band then there are no obvious model defects. So I want to say, if this residual points are distributed randomly, then this means there is no model defect. That means your assumptions of error equal expectation of EI equal to 0. These assumptions hold, as well as variance of EI equal to constant for all I. This is also because you see that in both sides of this line, points are randomly distributed. So this means expectation of EI equal to 0 as well as variance of EI equal to constant, because here we do not see any pattern. And in figure B, if plot is such that the residuals can be contained is an outward opening funnel, then such pattern indicates that the variance of error is not constant, but it is increasing function of y. And here in figure C, you see that if the plot is such that the residual can be contained is inward instead of outward, it should be inward. Inward opening funnel then such inward opening funnel, then such pattern indicates that the variance of errors is not constant, but it is a decreasing function of y. If your residual plot look like figure B, then you can say that it is the increasing function of y, and if your residual plot look like figure C, then you can see that your error variance increasing function, decreasing function of y. Okay, and if such thing is happening, the remedies we already mentioned for simple linear regression setup. Here we also use same remedy, that is use suitable transformation to either the explanatory variables or study variables, or use weighted least square method. So that is either you use suitable transformation applying on either explanatory variable or explanatory variables or study variable, and or use weighted least square method. And we note that the transformation on study variable are generally employed to stabilize the variance. Okay.
Okay, so transformation used for stabilization of variance. Now if your figure look like if your residual plots look like this, then this means if plot is such that the residuals can be accommodated inside a double bow, inside a double bow, then such pattern indicates that the variance of error is not constant. This indicates that in such pattern indicates that the variance of error is not constant, but y is proportional between your study variable. Y is proportional between zero one, 0 and 1. The y here then y may have, so y may have a binomial distribution. The variance of binomial proportion near to 0.5 is greater as compared to near to 0 or 1. So the assumed relationship between y and x is non-linear. So if your figure is look like, in that case your y is binomial distribution. Y has a binomial distribution. The variance of a binomial proportion near 0.5 is greater as compared to near 0 or 1. So the assumed relationship between y and x is non-linear. Okay. So and here also we use same remedy, suitable transformation and or weighted least square technique. Okay. And if your residual plots look like this, that means your assumptions of linearity does not hold. And this means the assumed, this means there is a this means y and x are there is a non-linear relationship between explanatory variables and
study variable, and moreover this means that this could also mean that some other explanatory variables are needed in the model for example, square error term may be necessary, and in that case the remedy is transformation on explanatory variables or study variables, and this may help for this situation. So in that situation we use transformation of variables. Moreover, note that a plot of residuals against yi hat may also reveal one or more unusually large residuals. Again I repeat this point. A plot of residuals against yi hat may also reveal one or more unusual large residuals. These points are potential outliers. These points are potential outliers, large residuals that occur at the extreme yi hat values would also indicate either the variance is not constant. Large residuals that occur at the extreme yi hat values could also indicate that either the variance is not constant or the true relationship between y and x is nonlinear. Okay, so please write this note. This possibility should be investigated before the points are considered outlier. So I repeat this point. Please write this note. Write these points. A plot of residuals against yi hat may also reveal one or more unusual large residuals. Full stop. These points are potential outliers. Full stop. Large residuals that occur at the extreme yi hat values could also indicate that either the variance is not constant or the true relationship between y and x is nonlinear. This possibility should be investigated before the points are considered outlier. So we need to investigate this thing. Okay. Okay. Okay, Shubhrojit. So before declaring whether this is a potential, this is an outlier, we need to check this thing. So can I go to the next slide? Please tell me, Shubhrojit. If you finish this thing, please tell me. Okay. Now it is okay? Okay, thank you, Shubhajit. So, similarly, we can do same thing. Uh, we draw the plots residual against explanatory variables. We need this thing also. Plots of residuals against explanatory variables. And this is also helpful to find out the whether find out the adequacy of the model. So please write down the points. One I mentioned point one by one. Consider the residual on y-axis and values of jth explanatory variables, not variable. Xij and I from 1 to n on x-axis. And this is the same way as we have plotted the residuals against yi hat. And in place of yi hat, here we consider xij. So this is, instead of yi hat, I use xij in x-axis, and this is a residual in y-axis. And the interpretation of this plot, as in the case of the plots of residual versus yi hat, same interpretation, same way you can interpret this thing, and this is as follows. And see that instead of yi hat, suppose you use xij in horizontal axis and all 5 figures, and you exactly the same way you can explain these all 5 plots. That is, in figure A, if your residual versus explanatory variable, suppose first explanatory variable look like figure A, in that situation you can say that there are no obvious model defects. And if your residual versus explanatory variables, your figure look like figure B, then you can say that your variance is not constant. Even you can get same explanation for figure C also, and figure uh, if your residual versus explanatory variables look like figure D and figure E, we can say that uh, if your uh, residual versus fitted value, uh, residual versus explanatory variable plots is look like D, then you can see that your variance is not constant, and in that case you need to use suitable transformation. And the remedy for these three cases, figure B, C and D, is a suitable transformation. And if your figure look like E, in that case you see that there is possibilities, the possibilities like the possibilities like Y may be a proportion higher order term is xi of a higher order term of xj. Proportions y may be a proportions of higher order term of xj, that is for example xj square. Suppose your explanatory variable is x. If you use x1, then you should write x1 square and so on. So in that way you have a idea from each explanatory variables, from the residual part of each explanatory variables. If you have an idea whether y is directly related with xj's or not. If not, what is the remedy? In that way we can build a model. Okay, Subhrajit. So you write a note 1. In the case of simple linear regression, is right. In the case of simple linear regression, it is not necessary to plot residual versus yi hat and explanatory variables. Residual versus explanatory variable. The reason is that the fitted values yi hat are linear combinations of the values of explanatory variable xi. So the plot would only differ in the scale for the abscissa or x-axis. Next note, it is also helpful to plot the residuals against explanatory variables that are not currently in the model. So please read this line carefully. It is also helpful to plot residual against explanatory variables. Those are not currently in the model. Suppose you use x1, x2, but my suggestion is you also plot residual versus x3, x4. Suppose x3, x4 are the another explanatory variables which are not used in the model. My suggestion is you also plot the residuals versus those explanatory variables those are not used in the model. Okay, so but which could potentially be included any structure in the plot of residual versus an omitted variable indicates that incorporation of the variable would improve the model. This is the last note for today's class, and I want to stop after this note, and we will continue this class on Thursday, same time 6 p.m. So note 3, this is the last note for today's class. Plotting residual versus explanatory variable is not always the most effective way to reveal whether a curvature effect or a transformation is required for that variable in the model. And in that case, partial regression plot, we will discuss this on coming Thursday class. Partial regression plots are effective in investigating the relationship between the study variable and explanatory variables. Okay, so we will continue this topic, adequacy of model checking, uh, checking of adequacy of the model. So we start with partial regression plot and then we go one by one other portion of this topic. So please join our next class Thursday on same time 6 p.m. coming Thursday please, at 6 p.m. So we'll continue this thing. So please tell me if you have any question. Otherwise I close this thing. Okay. So Suprajit, Oyun, Bishari, Chundrima, and anybody who watching this video, please tell me, have you any queries regarding the portion which I taught today? Thank you for watching this video and stay with us. So have you any question? Okay, Shubhrojit. Okay, Chandrima. So now I am going to end this string. Okay. Thank you everybody. Thank you. So please join the